Hello everyone, welcome to Degree Concepts Physics classes. Today we will be discussing about Kepler's laws of planetary motion, which in earlier classes I have told a brief details about Kepler's laws, and even we have discussed about what are the three laws of planetary motion, and also what is the relation between the conservative force and potential energy, how we can express conservative forces as negative gradient of potential energy, and we have seen some derivations also, and we have seen three laws just in brief. But in today's class we will be learning about the detailed explanation regarding Kepler's laws of planetary motion. Myself as Vidyarani, working as Assistant Professor of Physics at MBS Government Degree College, Autonomous, Mehboob. Let's start our session. So this I just a pic I am showing here. So here the sun is there. So here there are the 8 planets which are revolving in their orbits around the sun. So we will be learning about these planetary motion using Kepler's laws of planetary motion. First, let us know who is Johannes Kepler. So this man is behind designing the laws of planetary motion. He is Johannes Kepler. He was born on December 27, 1571 in Germany. He studied about the planetary motion of Mars, so used observational data of Bray. So he studied this planetary motion of planet Mars, not Earth. So he used these observational data of the other scientist called Bray. So again one more visual I want to show you. So this is the sun here. See here, so 2 planets are revolving around the sun in their orbits without falling into or falling outside their orbits. So how this is happening without these planets are moving in their orbits continuously without attracted towards the sun or without falling out of their orbit. Let us see. First, let us know about the history behind the planetary motion laws. So, Johannes Kepler was a German astronomer and mathematician of the late 16th and early 17th centuries. Kepler was born in Württemberg, Germany in 1571. His parents were poor, but he was sent to the University of Tübingen on a scholarship in recognition of his abilities in mathematics. This is the life history of Johannes Kepler. So, this is the background story of his. So he, because his ability in mathematics was so mesmerable, so he was sent to the University of Tübingen. So unlike Bray, Kepler believed firmly in the Copernican system. In retrospect, the reason that the orbit of Mars was particularly difficult was that Copernicus had correctly placed the sun at the center of the solar system, but had erred in assuming the orbits of the planets to be circles. Thus, in the Copernican theory, epicycles were still required to explain the details of planetary motion. So, unlike Bray, Kepler believed in the Copernican system, that is heliocentric subject, that sun is the center of all the planets and all the planets are revolving around the sun in circular orbits, which was given by Copernicus. But whereas this Kepler believed that even though the sun is at the center of all the planets, even though the planets are revolving around the sun, but they are revolving not in the circles, but their orbits are of the form of ellipses, not a perfect circle. So this discovery he has made. So let us see. So Kepler's laws gives a description of the motion of planets around the sun. So these laws help us to understand how the planets are moving around the sun. So let us see a look about Kepler's law. Kepler's laws is these laws are derived by Johannes Kepler. So Johannes Kepler has given 3 laws. The first one is Kepler's first law, which is also called as law of orbits. So second one is called Kepler's second law, This law is also called as law of areas. And Kepler's third law, this law is called as law of harmonics or law of periods. So first law I have just now told. This first law is called as law of the ellipses. That is not the orbits are in the shape of circles, but the orbits of all the planets revolving around the sun are moving in the elliptical shape. So second law describes about the law of equal areas. That means in a given time interval, so the area swept by any planet moving in an orbit will be of equal areas in equal intervals of time. And the third law, that is called as law of harmonics, which tells us that the time period, the square of the time period of any planet revolving around the sun is directly proportional to cube of the area. The Kepler's laws are: the first law, if we observe, the orbit of every planet is an ellipse with the sun at one of its two foci. I have already discussed about the elliptical shape in detail, showing with a figure. So I will just show you once more with a figure. So let us say this is the ellipse. So this is the two foci at one. So according to Kepler's first law, the orbit of every planet is an ellipse, and the sun is at one of its foci, either at this point or at this point, not at the center. So the radius vector of a planet sweeps over equal areas in equal intervals of time. This is the second law. So, and the third law, if you observe, the square of the orbital period, that is t square, is directly proportional to cube of the semi-major. Cube of, let's say this is the same major axis and this is the minor axis. So semi-major axis means from the center point to the one end of the foci, that is A. So let us say this is semi-major axis. So the square of the time period is 3 times the cube root of cube of the semi-major axis. That is t square is directly proportional to a cube. So derivation from Newton's laws, if you see, Isaac Newton solidified Kepler's laws by showing that they were a natural consequence of his inverse square law of gravity with the limits set in the previous paragraph. Further, Newton extended Kepler's laws in a number of important ways, such as allowing the calculation of orbits around other celestial bodies. The solutions to the two-body problem, we have already seen the two body problems and one body problem, where there are only two particles involved, say the sun and one planet, can be expressed analytically. These solutions include the elliptical Kepler orbits, but motions along other conic sections, parabolas, hyperbolas, and straight lines also satisfy Newton's differential equations. And next, the solutions deviate from Kepler's laws in that the focus of the conic section is at the center of the mass of the two bodies rather than at the center of the sun itself. The period of the orbit depends a little on the mass of the planet. So firstly, if you observe, the orbit of every planet is an ellipse with the sun at one of the two foci. An ellipse is a particular class of mathematical shapes that resemble a stretched out circle. We have already seen. So if I'll show you with a figure. So let this is a circle. Assume that this is a circle. So elliptical will be little bit stretched outside. Ellipses have two focal points, neither of which are in the center of the ellipse, except for the one special case of the ellipse being a circle. So for this there won't be any center, but two foci will be there on either side of the major axis. Let us say this is the major axis and this is the minor axis. So there is one foci here and there is one more foci on the other side. Circles are a special case of an ellipse that are not stretched out, in which both focal points coincide at the center. But in case of circle, if you observe, both the focal points coincide at the center. Hence the circle doesn't have focal points, but instead it has a center. So next, eccentricity. I have already discussed about eccentricity. Eccentricity of an ellipse is defined as the ratio of distance between foci to the length of the major axis. In the figure below, if eccentricity is denoted as E, the distance between the foci as C and the length of the major axis as A, the formula is given by, so this is the formula given by the eccentricity. So let's say, so I have shown you here in the figure. So this is the major axis. So the sun is at one of its foci. So the nearest point to the sun is called as perihelion. The farthest point on major axis from the sun is called as aphelion. I have already discussed. This will be equal to, this distance will be equal to A into 1 minus E, whereas this distance is equal to A into 1 plus E. So E is given as C by A. So between the foci is, the distance between the two foci is called as C, and the length of the major axis is called as A. So E is equal to distance between the two foci by length of the major axis A. So see, these are the two focus of ellipse. So there is sun here. So planet is revolving around the sun in elliptical orbit. Kepler's first law is illustrated in the image shown above. The sun is not at the center of the ellipse. We have seen that the center, there is no center. That means there is no sun is not at the center, but it is instead at one focus. Generally, there is nothing at the other focus of the ellipse. Only on one of the focus the sun is there, but the other focus there won't be anything. The planet then follows the ellipse in its orbit, which means that the Earth-Sun distance is constantly changing as the planet goes around its orbit. So that means, so because this is an elliptical orbit, the distance between the sun and the earth will be changing. If the earth moves to this place, so the distance is different. If the earth has moved to this place, the distance between the earth and sun will be of different value. And if the earth has moved to this point, so from this point to this point, that is from the distance between the sun and the present position of the earth, will be of different value. That means the distance between the sun and earth is constantly changing because of the elliptical orbit. So the planet then follows the ellipse in its orbit, which means the Earth-Sun distance is constantly changing as the planet goes around its orbit. So for the purpose of illustration, we have shown the orbit as rather eccentric. Remember that the actual orbits are much less eccentric than this. Therefore, when C is nearly to A, the ellipse appears to be flattened. So E is equal to C by A we have taken. When C is nearly equal to A, that means the ellipse appears to be flattened. Flattened means, so the both become equal, means E B will be nearly equal to 1, which is nothing but a perfectly circular shape. When E is smaller than A, the ellipse appears rounded. When C is smaller than A, the ellipse appears rounded. When C is 0, the ellipse become a circle. When C is 0, that means there won't be no distance between the two foci. That means two foci are at the same place. That means the ellipse becomes a circle. I will show this point with a circle. So this is the circle. Let us think. I have told that two focus will meet at the same point called center. So two points are meeting at the same point. That means the distance between the two focus will be of 0. That is, C will be equal to 0. When C is equal to 0, eccentricity will become E is equal to, we know that C by A. That means C is 0 here. So 0 by something is also 0. That means no eccentricity. So no eccentricity means as C value is becoming less than the A value, the ellipse will try to appear as much rounded as possible. Then when C is equal to 0, automatically eccentricity is also becomes 0. That means that ellipse is a perfect circle. So now let us see the eccentricity. So eccentricity is the degree of flatness. So eccentricity is equal to 0, which means that perfect circle. So Earth eccentricity is 0.017, not perfectly circle. So hence we assume as elliptical. So E is equal to C by A, that is C is equal to center to focus. So center to focus is C. A is half of major axis or semi-major axis. So this is A. So this is how we will count. So the distance between the foci, that is C, the major axis A and the minor axis B, can be solved using the Pythagorean theorem called C square is equal to A square minus B square. The distance between the foci is C, the major axis is A and the minor axis is B. So this can be solved using C square is equal to A square minus B square. That means if you observe here, if we draw so from here to here it is C. So and this is A, we know that semi-major axis, and minor axis is B. So if we draw joining these 3 points a triangle, this is, I am not able to draw perfectly, but please understand. So this will be the hypotenuse, right, of right angle triangle. So this value is equal to C square is equal to A square minus B square. So this is how we can show. C square is equal to A square minus B square. And next, see if you see here, this will be better understand using figures. So the Earth is here, the distance is more between the Sun and the Earth. When the Earth reaches to this point, the distance becomes less, and here to this point the distance has become more. So the distance between the Earth and the Sun is constantly changing. And one more point, if you observe, so when the Earth is far away from the Sun, it is moving slowly, but when it is nearing the Sun or when it is near to Sun, that means then it starts moving very fastly. See, you might have observed, so when it is here it is moving little bit slow, but when it reaches to this point or this point it is moving very swiftly. So that means the velocity increases as the distance between the planet and the Sun decreases. So second law, let us see, the radius vector of a planet sweeps over equal areas in equal intervals of time. So the radius vector of a planet sweeps over equal areas in equal intervals of time. Let us know about this. So radius vector is an imaginary line connecting the Sun and the planet. So radius vector is not a real line, but it's an imaginary line which we are assuming that it is connecting the Sun and the planet. See here, if you observe here, let us say this is the area covered in this time interval of time. In the same time interval of time here, let this be this area. So when you see these blue areas, when you compare these two blue areas are of same value, because in equal intervals of time this radius vector sweeps equal areas. So hence in equal interval of time, whether the planet may be at any place, but at a time period, what happens, the area covered by the planet will be of same value when we compare with the other area of same interval. So Kepler's second law is illustrated in the preceding figure, that is we have seen the above figure. The line joining the Sun and the planet sweeps out equal areas in equal times. So the planet moves faster when it is nearer the Sun. Thus a planet executes elliptical motion with constantly changing angular speed. Speed is changing means angular speed is also changing because it is rotating. So changing angular speed as it moves all about its orbit. The point of nearest approach of the planet to the sun is termed as perihelion. I have just now told that when the distance of the sun and earth is very less, that means that nearest point is called as perihelion. The point of greatest separation is termed as aphelion. Hence, by Kepler's second law, the planet moves faster when it is near perihelion and slowest when it is near aphelion. You might have observed in the perihelion place, so that means when it is near to the sun, the planet moves with a very high speed when compared to when it is at the aphelion place. So near the perihelion, the planet moves faster. When it is near to the aphelion side of the sun, then the planet moves little slow. So Kepler's second law, we can show it as visual. If you observe, so at a particular interval of time, so here it is moving faster, but at a particular interval of time the area is same. At any two given points of same interval, if you observe, the area remains, A is not changing, though the points where the planet moving is changing, but the interval of time is not changing, hence the area is not changing. So Kepler's second law is equivalent to the fact that the force perpendicular to the radius vector is 0. The area velocity is proportional to angular momentum, and so far, for the same reasons, Kepler's second law is also in effect a statement of the conservation of angular momentum. So Kepler's second law is also can be said an effect of the statement called conservation of angular momentum. So the aerial velocity is proportional to angular momentum. Hence we can say that conservation of angular momentum takes place in place of planetary motion. See here again. So these are the different areas in a particular interval of time covered by the planet. But these areas of different plate points but of equal intervals is same, because in equal intervals of time the planet sweeps equal areas. So when are we closest to the sun? So when our earth reaches to the perihelion point, then we can say that we are closest to the sun. So about January 4th, by about 1.5%, not enough to make the sun look different. So almost on January 4th we will be moving closer to the sun. So third law we will see. The square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. So the square of the orbital period is t square, and cube of the semi-major axis is semi-major axis is a. So a cube of the semi-major axis is a cube. So t square is directly proportional to a cube. So if you observe here, this is perihelion point, this is aphelion point. Here the sun is at one of its foci. Let us say this is the major axis and this is the minor axis, and this center of the ellipse to the one side of the perihelion point is called a semi-major axis. So according to Kepler's third law, this third law is also called as harmonic law, because Kepler enunciated it in a laborious attempt to determine what he viewed as the music of the spheres, according to precise laws, and express it in terms of musical notation. He has also called it as music of the spheres because, and it is also called as harmonic law because he tried to express these third law in terms of musical notation. Symbolically, p square by planet by a cube of any planet is equal to p square of earth by a cube of earth. So both are directly proportional. So we can equate p square of any planet by a cube of any planet is equal to p square of earth by a cube of earth, where p represents the time period and a represents the semi-major axis. So if you observe here, so one of the planet is revolving in this way and the other planet is revolving around the sun in the longer orbit when compared to the first one. So how they are moving from one another, if you might have observed here. So this is how we can explain all three laws of planetary motion using Kepler's laws. So these laws helped us very much, because before Kepler discovered that the planets are not revolving in a circular orbits around the sun, all the scientists throughout the world have assumed that the planetary motion is in the form of circles but not ellipse. But Kepler changed it in a way that he discovered that the planets are moving in an elliptical orbits. So not the earths or the planets are revolving in a perfect circular orbits, but because of the eccentricity has proved, all the planets are revolving around the sun in elliptical orbits, keeping the sun at one of its foci. And the second law, he has also discovered that in a particular interval of time, the radius vector sweeps equal areas at all times. So, and the third point is that the square of the time period is directly proportional to the cube of the semi-major axis. In this way, he discovered three important formulas which helped us the planetary motion in a better way. And whatever experiments or whatever we are exploring today in space is because of the impression given by Kepler's. Hence, Kepler has given us great information, or as well as a great information to know about the planetary motion. Thank you one and all for today's session. Signing off.